Anyway, let's start recording. And full screen. Oh, and also assignment is due tomorrow, but in fact some people have already submitted, so that's very fast. And I guess this is the last thing that we want to discuss about is the entanglement and Bell inequality. If there is enough time at the end, we're going to talk about something which sounds a bit more cool, which is teleportation. So let's see how much time we have. And again, this one is not covered in the exam, right? The whole point for me in the last lecture is just to explore some interesting stuff and to see why people always say quantum mechanics is like exciting and things, and then we spend the whole semester calculating bras and cats and it feels very boring. But we return to the original reason why quantum mechanics is weird to many people. Okay, so on Monday's class, am I recording? Yes. Yes. Yeah. So on Monday's class, I was telling you about the EPR experiment, right? So just now the video was re-explaining the EPR experiment again, and the EPR experiment, Einstein, Podolsky, and Rosen experiment has forced us to confront, right? Either it seems like we have two choices: locality or the superposition, right? So it forces us to reconsider. So what are we supposed to reconsider? Maybe the quantum superposition is not real. So it's not actually happening, right? So this is the philosophical thing. Does the state exist, right? Is the cat dead or alive before you observe it? Okay, that is the weird thing, because if you have this entanglement particle, right, that is entangled. That means, and that is reasonable to be entangled because we want to conserve angular momentum. Okay, so if the state hasn't been decided whether it's up or down before measurement by Alice, but the instant Alice measured, it will determine the state. But that means the outcome is also determined on the Bob side. Even though Bob is very, very far away, you can do this experiment in a different planet. So does that mean that the information has communicated faster than light, instantaneously towards Bob? Okay, so that sounds ridiculous, right? If we learn special relativity, we say nothing can travel faster than light, locality. So that means, in other words, maybe it is not actually superposition. Maybe the state is already existing, we just haven't observed it yet. Right, so that means the particles state are already decided or fixed. We just don't know it yet. Okay, so that means the main point is this was Einstein's proposal, because Einstein is the person who set up relativity. He believes in locality, right? So nothing can travel faster than light. So therefore, there must be some. If the particle state already exists, that means there must be some mechanism to determine the state. Okay, so that is the idea. So some mechanism to determine the state before measurement. So that is the key point. Okay, and we call this the hidden variables. So this section is going to be something pretty cool, because even though we don't know it yet, right? Because quantum mechanics is the theory of quantum mechanics is not powerful enough to predict what is the state. We can only say at what probability we get this state. Okay, so that means there must be some powerful theory. We just don't know it yet. But the genius of John Stuart Bell is that we can even get some conclusion even before deriving the hidden variable theory, because this is just the hidden variables. We don't know what is this theory, and that's the whole problem we have to begin with, right? But even in this situation, even if we don't know what is the variable is hidden, we can still come up with an experiment about it. So this was proposed in 1964. John Stuart Bell proposed an experiment that we can to check whether is it hidden variable or superposition, right? So is another thing. Okay, so it's basically a generalization of the EPR experiment. So we it proposed so John Stuart Bell is proposed an experiment to check for hidden variables. Okay, so basically it is a generalization of the EPR experiment. Oh, talking about exams, right? Yeah. So the EPR experiment, so it is a generalization. So what we have here is we still have a source of entangled pairs. So we got a source of particle pairs, entangled or not, but obviously we want to check the case where it's entangled, right? So it will go to two sides. Alice is standing here, Bob is standing here. So Alice has, let's say we are talking about the spin half particles. So Alice have a Stern-Gallac magnet, and we have, even though this chapter is not in the exam, but we did learn in chapter 7, which is in the exam, that if you want to measure the spin in a direction of a vector m, then the spin measurement operator is m dot sigma. Okay, so this is a Stern-Gallac magnet with m dot sigma. So Alice can choose what direction to put the magnet in. And then as we have learned, the eigenvalues of m dot sigma is either +1 or -1. So +1 means the particle is up in the direction m, and if it's -1, the spin is down in direction m. Okay, so this is Alice, and the outcomes, just to enforce and drill down the situation, is either it's supposed to be eigenvalues of m dot sigma, and we have calculated the eigenvalues of m dot sigma. We did this in chapter 7. It's either +1 or -1. So there's as you can say, the sample space is -1 or +1, right? So there's two possible outcomes. And then same thing here, Bob, he can measure, he has his own Stern-Gallac magnet, he can measure his own direction. So Bob is here, and it can, yes, same story, going up or going down, right? So if it's up, that means the spin of the particle is up in the n-axis and down along the n-axis. So Alice and Bob, the generalization here is, in the EPR experiment, both of them using the sigma z. But for this case, we can change the direction of both detectors, and the outcomes is also same story, +1 and -1. Okay, so the idea for this experiment is to check for the correlations of both their measurement. Okay, so what we are doing is many particles are measured. Okay, and we record their outcomes in a table. So yes, so let's say Alice result, right, will be, let's call A for Alice, and if Alice is using the vector m, the direction m, then she will get a bunch of results, right? So let's say, I don't know, so let's say at first it's +1, and then she measure again, because it's, for us, it's probabilistic, right? We don't know what we will get unless we measure it. So sometimes she get +1, sometimes get -1, maybe -1 again, and then back to +1, right? And so on and so forth. So we collect all the data, and then we do the same thing for Bob's result. So Bob is over here, he is also doing his experiment, right? And then same thing, Bob also, this is a measurement, so we might get +1, we might get -1, but it is a certain probability. Okay, so we don't know. That's the whole point. We are not sure, right? So and so on and so forth. Okay, maybe yeah, it can be random. Okay, so it could be random based on any probability distribution, and we have learned how to calculate the probability distribution, right? The cat bra put it in. But the key point here is we record the product of A times B. Okay, so this times this is +1, this times this is -1, this is +1, -1, and so on and so forth. So we record this information as well. Okay, and then what we want to do is we want to find the correlation. So let us define the correlation first by we count. Okay, so let's say you do enough times already. After you finish a bunch of experiments, you get the number of experiments where Alice times Bob is +1. So number of experiments where AB is +1, right? So AB +1, that means yeah, so you count 1, 2, 3, 4. Okay, so you count how many of these, right? And then n minus also you count. When the multiplication gets -1, right? So yeah, so you count 1, 2, 3, 4, 5. You count how many, see how many there are. Okay, so we count all these, and then we define the correlation. So today we call it the Bell correlation, since he was the one who thought of this. Okay, so the Bell correlation is defined as CMN, right? Because our experiment will depend on what direction of vector that we choose, and we define as the number of the same results minus the number of different results divided by the total number of experiments. Okay, so that is our Bell correlation. So our correlation could be anything, right? Let's say by chance, purely by chance, we got some special cases. For example, if Alice and Bob always get the same result, right, for whatever reason, in case this happens, then the correlation will be equals to 1. So if all AB are +1, then none of them are different, right? So so this is 0, so that means the correlation between MN is equals to 1. So this is a correlated. Okay, but if for whatever reason all the Alice and Bob always get the opposite result, if Alice get down, Bob gets up, right? If -1, then CMN is -1. So we call this anti-correlated. Okay, so notice one thing, the difference between the EPR experiment, because you might be thinking, right, yeah, spin half is 1 up, 1 down, it's going to be always anti-correlated, am I right? But that is only true if both are using the sigma z. Okay, so if one is sigma z, the other is sigma x, then the probability will be different already. Okay, so we do not expect these two directions to be the same. So when these two directions are to be the same, then it will be the eigenvalue of that direction, this will be the eigenvalue of that other direction. So that is why in general, it could be some number between -1 and 1. Sometimes I'm lazy to write the arrow vector because it takes forever to write. Okay, so you get the point, right? I hope. So this is the correlation. It will be some number between -1 and 1. Okay, so here is the thing, right? So this is just the setup of how one might do the experiment. But now let's think about the hidden variable. Okay, because at the moment, right, whether or not to get 1 +1 or -1 is, if it's a quantum superposition, there is no way to predict it, right? So but if there exists a hidden variable, So we call it lambda in most textbook, right? So let's say there's a hidden variable that determines the state before measurement. Okay, so that means no superposition, right? So but there's a state that it will depend on the hidden variable. We just don't know it yet. Okay, so then the function a and b, right, is a function should depend on lambda as well. Okay, so that means my function a is a function of the direction, right? It depends on what vector you measure, and then it depends on lambda. So the output of the function is either give you 0 or +1, right? And same thing for Bob's side. So it depends on what direction Bob is measuring, and if there's a hidden variable, then it depends on the hidden variable. So you got +1 or -1. Okay. And if there's a hidden variable, then we don't know, but there should be some probability density. So we're going to define rho. So rho of lambda be the probability density of the hidden variable. So what is the probability that the lambda is this value? What's the probability that the lambda is this value? Because we don't know, right? The experiment is probabilistic. So if it's a probability, then rho is a function. The function of rho is going to be some number greater than 0, and the integral of rho over lambda must be equals to 1. Okay, so we got this. Rho now. Mn. No, so Mn are the direction of the SG magnet. And the N is the direction of Bob's magnet. Okay, so yeah, in case anyone comes in late, this is the experiment, right? I have two particles, one going left, one going right. This left one will go to the SG magnet that is along the M direction. Then this magnet is along the N direction, right? And it has their own corresponding two outcomes. Okay, so we got this now, right? Then if this is this probability distribution, then the correlation between A and B can now be derived by this formula. So the correlation between N and N is the is the integral of the, so A times B, right? It depends on lambda and it depends on lambda, but it is a probability distribution, right? So so we need to integrate over what is the probability of the product, and we integrate with respect to lambda. Okay, so this is the probability, and it's the same as what we will do when you actually do the experiment, right? We want to count the correlation, then we need to do this, right? So this is by counting, but this is the theoretical origin of the correlation. Okay, so I guess you can say that in statistics, right, the more experiments you do, the closer this number is to this number, right? Okay, so so the key point is we want to check the locality and things like that. So therefore Alice and Bob, they are very far away from each other, so they can't talk to each other. So we let Alice and Bob choose their SG magnets independently. Magnets separately. Okay, so in other words, M is independent of n. Okay, I'm running out of ink. So can this last until the last lecture? That this is the last lecture already, so can this like finish off or not? So Cmn, right, is the integral of rho lambda. Actually I already wrote this down. Why am I doing this again? Okay, yeah, Alice, well, we emphasize this. Alice choose M and Bob choose N, and they do not agree previously what direction they choose. They just choose it on their own. Okay, so now let's do the experiment again. We repeat the experiment, but Bob choose a different direction. Okay, Alice don't change anything. Okay, so she keep it the same, don't touch anything. Now Bob choose a new direction, so let's call this n prime. Okay, so after finish one round, okay, Alice wait, just stay there, and then Bob will change to a new direction, and Alice doesn't know what is direction Bob is doing. But we can do that after that. Okay, start the experiment again and start measuring, and we try to calculate the new correlation. So this time the correlation is now with n prime. Okay, so therefore it is the integral of rho lambda Alice m lambda and b n prime lambda. Integrate this with respect to lambda over the probability distribution. Okay, so now what we want to do now is, okay, it's a good idea I wrote this again. So now I can call this equation 1 and call this equation 2, and I calculate the difference. Okay, so 1 minus 2, so Cmn minus Cmn prime is equals to this minus this. Okay, so the only different term here is the b with the different n direction. Alice still keeps the same direction, so therefore what we have here is a m lambda, b n lambda, and then minus a m lambda, and then b n lambda. Okay, so here we do another dirty trick. We say this is 1, okay, fine. But remember, what is b? The function b, right, and a is a function where the value is either plus 1 or minus 1. So therefore, b squared is equals to 1. So the dirty trick is, okay, 1 is equals to bn lambda square. So whatever this is, right, we don't know, it's a hidden variable, but it's either plus 1 or minus 1. So when you square it, you definitely know it's going to be 1. Okay, so therefore this thing now becomes what? So rho lambda is a m lambda, b n lambda, and then minus a m lambda. There's a b square, and then there's a n prime lambda, and integrate this with respect to lambda. So now I can factorize this out. Okay, so this is 1 minus, so I factorize this out, I am left with b n lambda power 1, and then n prime lambda lambda. Integrate this with respect to lambda. Okay, so and then another thing we can exploit about this, what is the absolute value, what's the magnitude of this? So here right now today we don't need to worry about complex numbers because all these are just normal integral, right? Just regular calculus, and what we have here is either plus 1 or minus 1, right? The correlation a times b is either plus 1 or minus 1, and this term a times b is also plus 1 or minus 1, and 1 minus, well, whatever this is, this number is definitely positive, right? If it's 1, then you get 0. If it's minus 1, you get 2. Definitely positive. So the main point here is the absolute value here is going to be, what is the absolute value? So if this is plus 1 or minus 1, right, the absolute value of this thing, rho lambda a m lambda b n lambda, okay, and then times this bunch of stuff, the absolute value of this is going to be greater or equal to smaller, right? Is 1 or minus 1, it will be smaller than this integral without this term. So it's just bn lambda bn prime lambda. Okay. Yeah, we need to think a bit, but this is a bit of calculus math, but you can see this integral. Let's say I integrate this function, right? This is a positive number, but this is either plus 1 or minus 1. If it's minus 1, it will make the thing smaller, right? Then if it's plus 1, it make it bigger. So if it's just always 1, then this integral will be larger than this integral. Am I right? Okay. In fact, if it's always negative 1, that you just become a negative integral of the previous one. So the magnitude of this is smaller or equal to this, right? If it's sometime plus 1, sometime minus 1, it will make the area under the graph smaller, right? So what we have shown here is, what is this? This actually equals to this. So the magnitude of Cmn minus Cmn prime is smaller or equal to this integral, rho lambda 1 minus b n lambda b n prime lambda. Integrate this with respect to theta. Okay, so in other words, let me write one more line and open up separate the two terms. So this is integral rho of lambda with respect to lambda, and then this is the integral of negative rho lambda b n lambda b n prime lambda with respect to lambda. Okay, a few more tricks I'm going to put in, but this one is not much of a trick. This is just one. The trick here is to notice that b, right, b n lambda is negative a n lambda. Do you agree? Because, right, Alice and Bob choose two different directions, but if Alice and Bob both choose the same n, then the entangled particle is like the EPR experiment again. That means Alice get 1, Bob will get minus 1. If Alice and Bob choose the same n. Their results are correlated. Okay, so if Alice and Bob choose the same n, so therefore this term is actually, what we have here is 1 minus, well, minus minus becomes a plus, rho lambda, and then I got a n lambda b n prime lambda d lambda, and this is actually the correlation n n prime. Okay, so what we have found here is that 3 we have derived an inequality among the correlations. Okay, so yeah, the more I look at this, the more we think about this, the more like we appreciate how ingenious this experiment is, because I guess I should write it down first. Right, so C n prime. So this is an inequality among the correlations, and we call this the Bell inequality. Okay, so now why did I say that this is a pretty impressive result? Because John Bell, and until today we don't, even if there exists a hidden variable, we don't know it. That's the whole point, right? We only have quantum mechanics. So there's some hidden variable. There's no way to know it. At least we don't know it yet. But if a hidden variable such exists, then through this reasoning, we arrive at this formula. Okay, and that means the main point is we derive this using the hidden variable. So if a hidden variable exists, it must obey the Bell's inequality. So if hidden variable exists, right? Remember, the whole thing is hidden variable is to say that there's actually not superposition, right? What our language of superposition, we say some fancy things, but actually is not true, right? The cat is really dead. We just don't know it yet. Just that we don't know the variable, not because it's a really both dead or alive. Okay, so if the hidden variable exists, then Bell's inequality must be satisfied. Okay, so this Bell experiment introduced a criteria. Okay, a quantitative criteria is a formula. Okay, two numbers, you just need to check who is greater than the other. It is a criteria that is obeyed by a hidden variable and or superposition quantum mechanics. Okay, so previously I've been saying that whether the superposition exists or not is a philosophical problem, is for philosophers to just think randomly about blah blah blah, right? But John Bell actually put this in a precise mathematical statement. So it's not philosophical anymore, right? He brought this to something that we can really check. It is two numbers, and all these numbers can be measured in experiment. Okay, so we can check this by measuring this, and this. Okay, so and what did the experiment say? People have done the experiment. So the experiment is looking at the pi meson, right? So the pi meson decay state. So if we're just using quantum mechanics, then our state is just 1 over square root 2, up down, and then down up, right? So the left side go to Alice, the right side go to Bob, and then using quantum mechanics. So you can do this. Actually, you can use the density matrix and things, but I don't have time to derive this, and it's not covered in the exam anyway. So let's just give the formula. The formula for correlation in this situation is CMN, right? N is equals to negative m dot n. Okay, so again, as you can see, right, if Alice and Bob are using the same direction, the correlation is -1, right? So if both are using the sigma z, Alice get up, Bob definitely get down. So it's always opposite. But if the two directions are not parallel or not perpendicular, has some angle, then it will be the eigenvalues of this. So you do the calculation, it will be having some probability distribution. The correlation will not be perfect 1, but it will be some number in between, +1 or -1, right? So unless both of them use the opposite direction magnet, then plus up for Alice and plus down for Bob, so then it becomes correlated. Okay, so yes, so this is something that we can actually do. So we perform the experiment. With what? So the first round of the experiment, Alice choose the magnet in the, let's say, in the x direction, right? And then Bob puts the magnet in the j direction, right? So you do one round of the experiment, and then after that, the next round, Alice stay the same magnet, don't touch it, but Bob use a new direction. So let's say Bob put it in this way, I plus j. Okay, so we can now calculate all this now, right? So what is CMN? CMN, so CMN is just 0, and then what do we need? CMN prime, right? CMN prime is negative of this dot this, so it's -1 over root 2, and then CNN prime. So cnn prime is just this dot this, so it's also negative 1 over root 2. Okay. So now, so this is an experiment so that is another impressive thing, right? This experiment is actually quite easy to do. Well, difficult. You need to quantum lab, but the outcome of experiment, you just get +1 -1. So you just ask your grad student to just count, right? How many are the same? How many AB equals to 1? How many AB equals to -1? Just count, right? You can even use Excel to do it for you, and then you can get this. You will get 0. You get this. You get this, and then you will check the left hand side, right? So what is left hand side? So left hand side is CMN minus CMN prime, right? So this measurement will agree, this prediction will agree with the measurement. People have done this already, and it's just this number minus this number. So this number is just 0, minus -½ is 1 over root 2 absolute value, so it's just 1 over square root 2, or in other words, this is 0.707. Then if we check the right hand side of this experiment, right, so right hand side is 1 plus cnn prime, right? Yes, cnn prime. So this is 1 minus 1 over root 2. So this is root 2 minus 1 over root 2. So if you use the calculator, you get something like 0.293. Okay, so is this inequality satisfied or not? So if the hidden variable exists, the left hand side must be smaller, but look at this number. Okay, so at the moment, yes, I'm just doing this on paper, so this is a theoretical calculation. Okay, so you can do the experiment for real, and this can be confirmed. Okay, so in other words, like this situation, like this quantum system, this system, right? Yeah, this quantum system violates okay. So if you use quantum mechanics and if you use the pi meson decay state, this will happen. Okay, so it violates. So in this, if you use this model, right, then yeah, we cannot use the hidden variable theory. So the experiment was actually performed, but I don't think this initial experiment, I think they use atomic physics system. So it's not exactly the pi meson, but some other state that can do something similar, right? And the experimenters are Aspect, how to spell this name? Grangier and Roger in 1982. Okay, so that was the first time they performed this experiment, and it was a huge news around physics back at that time, right? Because from a philosophical question, whether the superposition exists or not, or like the state is not decided until you do the measurement, you get one outcome or the other, right? But before measurement, we don't know what it is, and it seems like it's actually happening. Okay, so this is what I just told you is a very, 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 very simplified model of everything. And of course, if you don't believe this experiment or this inequality, then people have kind of like make the inequality more precise, because we did use a lot of assumption in defining the hidden variables. So there is a CH-SH inequality and things like that, more sophisticated and using less assumption. And then later people test those inequalities using more sophisticated experiment and using better technology, right? This is 1982. So now in 2020s, people got even better quantum systems now, and now is normal to have quantum states that violate inequality. In fact, they even like categorize a list of quantum states that is how much does it violate the Bell inequality, and that will give us, that is what people used to say how quantum state is. So at this stage, it's pretty much well established that superposition indeed does exist. Okay? Yeah. So does anyone have any question? What time is it now? Okay, 4:42. So does that mean, well, since this thing is violated, right? Does that mean that the EPR paradox is really happening? That means an entangled particle go to two sides. If Alice does something, then instantaneously spooky action at a distance, Einstein said, it becomes to what Bob is expected to get. But so here's the thing, right? Is locality preserved or violated? Okay. Does that mean that information travel faster than light? Because if this thing can happen, right? If Alice does something and it instantaneously affects what happened on Bob's side, then does that mean that does that mean we can actually use this to somehow communicate faster than light? Actually, no, because we needed. Remember, right? In all this thing, we needed to calculate this correlation C. C, right? So CMN and CMN prime and etc. etc. And how to get the correlation? You need to do correlation by repeated experiments, right? So repeated experiments, and not only that, after you get the repeated experiments, we need to collect. We need to collect the data, and to check the correlation, we need to multiply the two numbers together, right? So what does that mean? That means Alice must still carry the data over to Bob, and both of them need to see the thing side by side, right? Then so this requires first of all, right, multiple experiments. Then collect the data from Alice and Bob. Right? Either they send it to each other or the third person collect it, but definitely you need to travel less than the speed of light. So that means requires so in quantum systems, people call it a classical channel. So classical channel is just a fancy way of saying just a normal communication, right? Like really normal, like WhatsApp or email or whatever. Okay, or WeChat. Yeah, you can't talk on WeChat faster than light, right? So or anything at all. So therefore, we can't still know faster than light communication. So that is also another weird thing. Like locality at first glance, like almost like violated, but still, there is a loophole. We still can't travel faster than light. So I guess one problem has been resolved, but another problem still hasn't really been understood yet, which is to say that, yeah, if superposition does exist, then what does that mean? And so on. What's the implication? So there's still a lot of questions that haven't been addressed yet, so to say. Okay. Page 4. Yeah. Does anyone have any question? What a quantum lab looks like. So last time I showed you the video about spin that took place in a quantum lab. I forgot already. And the quantum labs that I have visited, right, is usually, it depends on the type of system that people want to use. So like the aspect grandeur, they are doing the atomic physics model, so it's an atomic physics lab, and I think it's like some gas chambers and things like that. If people can entangle photons, so then you can have like an optical lab. So those lab, right, if you do quantum systems using photons and entanglement using photons, then the lab is just like the room with an optical table. Okay, so optical table is just like a huge table with many holes, because you can screw your optical devices on different configurations, almost like Lego, right? You put your laser here, you put your lens here, you put your beam splitter, and then yeah, you do arrangement to do all those things, and then you do the measurement. So next to the table, there's going to be some data recording device is attached to a computer. So someone will be sitting at a computer to record the data, and maybe there's an oscilloscope, right, to see those things. So that is the optical. The another thing about optical table, right, is not just any table. It is a anti-vibration table. So the table got some little spring. I don't know how it works. It's very high tech. That because, right, optical experiment is very sensitive. If you shake the thing a little bit, it will spoil the data already. Even like in the building, right, if there's a car driving by, that it will cause the vibration, they can sense it. So that's why they need the anti-vibration optical table. It's super expensive. Okay, so that is if you use the quantum thing. And then if you want to do other things like quantum computers, I will talk about that a bit more later, like using trapped ions. Then what you do is usually there is a gas chamber, right, all metal tubes all around it, also looking very high tech. And then there are like 6 beams of lasers, and what they do is what they call laser cooling, because if you want to have a quantum state, right, it must be as close to zero temperature, because temperature introduce mixed states. Okay, then it becomes a thermal state, becomes like a density matrix example that I show you with partition functions. So you need to cool the thing down, and the way to cool it down is to shoot laser in opposite direction, so the atom gets stuck at the center of the laser, right? So then that requires a high vacuum, so that will take place inside a very strong vacuum system. Yeah, that is all I know about labs. But as you know, I'm not an experimentalist, so I'm not very good at labs. Malaysia, not that I know of. I don't know. Not that I know of, but I think closest to here is Singapore. Singapore, there's a center of quantum technologies. Yeah, yes. This is the optical configuration I was saying just now, right? Beam splitter, and then this is a correlation counter, I think. No, it's either -1 or 1. So this number here, right, A is the outcome of Alice, B is the outcome of Bob. So it's the eigenvalues is either +1 or -1. So it's just these two integers. But A times B is also still -1 or +1. Yeah, so you can, how is it? Yeah, I'll show you. I think, can we imagine that this is an area? So this is a function that depends on lambda, right? So A times B depends on lambda. So as lambda goes from -infinity to infinity, you get +1, -1, +1, -1, right? So this will make the integral +1 or -1, +1 or -1, right? And if you integrate this, if you keep changing between +1 or -1, right, the area under the curve is like sometimes positive, sometimes it's negative, sometimes positive, sometimes negative. So if you integrate this, you get a smaller number, right? If it's just 1 all the time, that is the area under the curve. You know what I mean? So yeah. Correct. Yes, because the idea here is the hidden variable probabilistic is like your statistics and probability, right? So it's not the superposition quantum. It's just that the probability of the hidden variable is the same level as your throwing coins probability. And there is nothing weird about that, right? So that is the thing. But if you use the superposition with that probability, then that is also different. Okay, it's not to say replace the probability with another probability, but the hidden variable is try to explain the probabilistic nature of quantum mechanics by some unknown but ordinary probability. Yeah, I hope that makes sense. Because without the arrow, because sometimes I'm lazy to write. I rush too fast to write. It's supposed to be all with arrows. Okay, yeah, makes sense. Yeah, so if you're interested in quantum stuff, there are quantum labs in Singapore, Indonesia. I have no idea actually. I'm not working in this field. China definitely has. I've read a few papers from China, and Taiwan, I think. Japan, and the European countries. Okay, so should we take a break? It's 4:54. Yeah, might as well, right? So let's take a 10 minutes break, and then we got one presentation, and we got one last fun thing to talk about, which is the quantum teleportation. So let's take a 10 minutes break. Yeah, we can. We need money lah. The optical table is super expensive. This part I'm recording. Yeah. So the probability distribution you change once you observe it. So you have secret information, right? If your enemy observe your information, then you will know that your enemy got that information. So that is a very useful thing for quantum cryptography. So quantum cryptography, normally people hear people talking about Alice and Bob, and there's a third person, so they call it Eve for eavesdropper. So if someone eavesdrop your information, your probability distribution will change and you can sense it. So you can develop all kinds of protocols and techniques on all this. And then computation is computer, like how you add numbers, how you design software based on this. Okay, so but here today we focus on information, and I guess most of us don't even know what is classical information, right? So the original information theory is now should be called classical information theory. Okay, and basically is we represent information in usually we use binary numbers, but other people can, like other software and techniques, they use hexadecimal and things like that. But for most of the time, especially most computer software, information is stored in bits. Okay, so bits is a number that is a variable that is either 0 or 1. Okay, so if your information consists of a very long text message, right, then it has n alphabets, so you need n, not just n you need some number of bits, so n bits. So you got some information, the number is going to be x1, x2 until xn, right? So each of these numbers are either 0 or 1. So you got a string of numbers that are either 0 or 1. So that is classical information theory, right? So you can store all your information in terms of 0 1, and then if you want to calculate a number, if you want to do some calculation, right, like a calculator on the handphone, then there are ways to manipulate this to calculate your answer, right? So all our computers and calculators and gadgets and devices depends on this. So we can now that we know quantum states and quantum system, we can now go to quantum information theory. Okay, so the advantage of quantum information theory is that the bits, right, is either 0 or 1, but now we can use the states. So information is stored in instead of bits, people call this qubits. So qubits are the basic unit of information, and this qubits is usually some kind of two-state system. Okay, so information will, instead of 0 and 1, we now use the state, we now write this as a cat 0 or 1. Okay, but the advantage is that now we have superposition, right? We spent quite some time talking about the Bell experiment and things. So the new extra feature is that it can exist in superposition. So that means something can be a combination of A plus B1, right? So a bit cannot just be B or 0 or 1, but in a superposition between 0 or 1. Okay, so how do we do this in practice? Well, I already kind of mentioned this, right, about the lab stuff. You either use atoms or photons, or the Stern-Gallac experiment itself is a primitive quantum computer because you can use a spin half particle as qubits. So when people say 0, is you represent it by a particle that is in spin up, and the number 1 is a particle of spin down. Okay, so another way to represent this is using spin half, and if you want to store the data, right, then you need to store this quantum state somewhere. So typically, for example, just a theoretical example, an array of n spin half particles. I say ion here. This is one of the things that can be in spin half. They form n qubits. So let's say an ions, and this one I'm not really sure how they do it in practice, but yeah, they put some particle here, and then some particle here, and then some particle here. So n of them. Okay, so so this particle will be some state, right? Some state, and so on and so forth. State, some state. So the each one of them is either 0, 1, or superposition. Right? It's not just 0 or 1, but it could be any A or B. Okay. So now I'm gonna introduce multiple qubits without talking about tensor product because you guys haven't learned it yet. But don't worry, we don't need to use tensor product. What if I use 2 qubits? Right? So 2 qubits means there are 4 possible. This is n qubits. So n is a data of n points. If I have 2 qubit is the most common situation, right? And we have 4 possible basis combinations. So let's say the particle, if you measure, right, even though it's in superposition, but measurement will have 4 outcomes. So 4 possible outcomes. Either both are spin up. So we call this 0, 0, right? Just for simple. Don't need to write a cat twice. And then if I measure, maybe one is up, one is down. So one is spin up, one is spin down. So we call this 0, 1. And then one is down, one is up, right? So 1, 0. So we call this 1, 0. And then the last possibility is both are spin down, 1, 1. Okay, so we write this as 1, 1. Okay, so we have 4 independent outcomes. Then we have 4 possible states: 0, 0, 0, 1, 1, 0, 1, 1. Okay, so these form an orthonormal basis. Okay, so the basic example is 2, but if you get 3, you get more and more possible states and permutations, and you have higher dimensional Hilbert space. So if you're talking about 2 qubits, we have a 4-dimensional Hilbert space. 1 qubit is just 2-dimensional Hilbert space. We spent a long time studying that already, right? So an arbitrary superposition, an arbitrary state, will be a superposition of all these 4. So arbitrary pure state. Let's not even go to mixed state, right? That's a whole other mess, and we don't have time to cover this. So a pure state can be written as some coefficient plus this coefficient plus this coefficient, and the last one over here. Okay, so in general, we got so these are the states. What page is this? Yeah, I don't know if my mic is picking up, but outside my place is very noisy now. Okay, what time are we at? Any questions? Okay, so this one is going a bit about computers, because computer, right, is like you input the numbers and then you want to calculate a number and give you an output. So this is where quantum gates comes in, qubit manipulation. So these are quantum gates. Okay, and to write this, right, to make it easy, let us talk about 1 qubit first. So this one was spin up, right? Last time we write this, if you want to use a column vector, we do it this way, right? And then the spin down is 0, 1. Okay, so spin half can be used as qubit. So the Stern-Gallup, if you just look back, the Stern-Gallup magnets, the sigmas, they manipulate your system, right? So for example, sigma x is 0, 1, 1, 0, sigma y 0 minus I 0, and sigma z 1, 0, 0 minus 1. Okay, and these are the basic ones that we learned already in chapter 2. In quantum information, there's a new thing called the Hadamard gate. So H is given by I don't remember, 1, 1, 1 minus 1. Okay, so for example, sigma z, do you remember what does sigma z do to your state? If you feed in the spin up particle, right, it becomes spin down. So this is like a flipper, right? So if you put a spin up particle inside, a spin down particle inside, it becomes spin down. Okay, so if I put an arbitrary superposition, pass it to this sigma x, this is a gate, it manipulates the information, it changes this into 1, and then it changes this into 0. Okay, and we are very familiar with the sigma z gate. That was the very first magnet, the Stern-Gallup magnet. We didn't call it a gate back then, but in the context of quantum computer, it is like a logic gate in your logic circuit of computers. But it's the same as what we understood last time, the Stern-Gallup magnet. And what does the Stern-Gallup magnet do, right? So this acting on this, you just give you, this is the eigenstate, give you this, and then the spin down is the eigenvalue of minus negative, so you got minus this, right? So it manipulates the state. Then what happens if you put a state into the Hadamard gate? It will be so this state, if you multiply this matrix, you just get a over root 2, 0 plus 1, and then plus b over root 2, 0 minus 1. Okay, so using this, right, you can kind of manipulate the system, and you can try to construct many different quantum operations, right? We just want to manipulate data over here. So that is just for 1 qubit. 1 qubit is very boring because it's either up or down. Usually if you're talking about, like, you know, like hard disk size or your RAM, your memory, right, the larger the number, the better. How many gigabytes, so more numbers, so it's always worth to go higher, but I guess the highest, for now, let's go to 2 qubits. Okay, so if you want to represent data using 2 qubits, we have 4 possible outcomes, right? So we can write it in matrix form like this: 0, 1, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, and 1, 1, 0, 0, 0, 1. Okay, so these are what we call the computational basis. Right? Remember, measurement outcomes form a basis in Hilbert space. Okay, so you can measure either both 0, both up, and so on and so forth. There's a few more qubit gates, but since we are just getting a flavor, right, we're not really gonna seriously learn this in a coursework. So I'll just give you an example of a 2 qubit gate. The quantum version of a C0 control knot. So C0 is already existing in classical computer theory, but what this does is we're taking 2 qubits, right? So 2 qubits is like yeah, qubit 1 and qubit 2. The diagram of the gate looks like this. This is just the symbol for the gate, and what it does is it takes this and then does a B sum A. So this is addition mod 2. I know the physics student probably don't know what this means, right? Unless you studied this before somewhere. Some math student, depending on what courses you took, you might have seen addition mod 2, right? But it looks very weird, but I think the matrix form is a bit easy to understand. It's the diagonal piece here and then the off diagonal here. Okay, so this is the same effect as this. Okay, so these are some basic things about quantum gates, but actually quantum gate is not the main point I want to focus on today. We want to talk about teleportation. But before we do that, right, let us transform to a new set of bases. So this set of bases is called the Bell basis, and as you suspect, it will have something to do with the Bell situation that we discussed just now. So the Bell basis is defined to be this formula, 1 over root 2. It's just the superposition of 0, 0 plus and minus 1, 1, right? So you see the plus 1 is the pi meson decay. That's why we call it the Bell basis. But you can also create other independent forms like 0, 1 plus or minus 1, 0. Okay, so given this, I can produce phi plus or phi minus, psi plus or psi minus, and we will also need the inverse transformation later. So given the basis, how do you convert this back into your normal computational basis? Okay, so 0, 0 is 1 over square root 2. To get 0, 0, you 5 plus, you need to cancel the one at the back. So 5 plus plus 5 minus, right? If I want to get 1, 1, I want to cancel the 0, 0 from this equation. So I take 5 plus minus 5 minus, right? And then same story, if I want to get 0, 1, I need to cancel the one at the back. So I take psi plus psi minus, and then 1, 0. To get 1, 0, I need to do psi plus minus psi minus. Okay, so now I know how to convert from one basis to another, and these bases are, you can already see from here, but these are complete. That means any arbitrary state can be expressed as a combination of these two states. So they are complete and orthonormal. Right? So if we take one bracket with another, they will get 0 unless it's the same one. Okay. Now, because they are complete and orthonormal, and because I don't have time to go into the details, but they are complete and orthonormal, so there must be some operator corresponding to this, right? So there exists an operator okay, where the eigenstates are this, are eigenstates. So if they're eigenstates, then these are the measurement outcomes, right? Because eigenstates are basically what we encode as our outcome of measurements. Okay, but what does the operator look like? We don't have time to cover this. Okay, but these measurements are called, because these are the Bell basis, and naturally these measurements are called the Bell measurements. Okay, so the phi plus is from the just a quick comment. the state in the EPR situation. Okay. Okay, so does anyone follow so far? 10 minutes. 10 minutes left. So let's go to let's talk about the actual teleportation. This is I guess hopefully, you know, after we go through this, we kind of understand what is teleportation and things like that. Is it as dramatic as it sounds? Because the word teleportation, right, people say, like, you know, like from the movie, like those Star Trek, suddenly you disappear and then you appear in another place. Okay, but what is actually happening? What do we mean when quantum information people say quantum teleportation? It's not teleportation an object over, it's just a state. So it might sound a little bit boring. So Alice has some information. So let's say it's 1 bit. Okay, so let's say it's 1 bit of information, just like 0 or 1. Okay, and it is some unknown state. So let's just say it is A1 plus B, A0 plus B1. But the idea of teleportation is we want to send this information to Bob. Okay, so how do you send information to Bob? But using quantum mechanics. So the way to do it is first Alice and Bob share an entangled state, and for concrete, right, let's just say this entangled state is the first one, our EPR state. So that means we got the pi meson, right? So we got a pi meson, one goes to Bob, right, and the other goes to Alice. So right now we don't do the sigma mn measurement, right? We already settled that already. So take out the magnet, just give one to Bob, give one to Alice. Okay, so after they decay, this thing is gone, right, separated. This whole thing will be in the quantum entangled state. So 5 plus is 1 over root 2, 0 0 plus 1 1. Oh, the EPR one should be opposite, right? So I should say that this is psi plus. Anyway, it's some entanglement source now. Okay, so let's say for some reason we create this state, but Alice has this qubit, right? This qubit written here, and I want to send this information to Bob. So how do we do this? So just to make sure we keep track of everything that's going on, how many qubits does Alice have? So Alice has 2 qubits. Okay, so in particular, right, we are going to be very clear so we understand the problem. We have this state, right, and the left side of this state, right? Bob only has 1, the right side of. Okay, so this is the setup. This is our starting point. Okay, so what is the total state of the system? So the total state of the system actually, by the way, right, yeah, this is getting towards the end of class. If you're not interested in this, I think you can exit now. I've done saying everything about the exam. The announcement was at the beginning. The camera, yeah, the student ID card, everything. Then, yeah, then the 20% is from the content before the exam. The rest is after. So yeah, then the rest of today is just gonna finish this off. So if you're not interested, you can exit now. Okay. Then I will, and also remember the assignment on Friday. Okay, back to where we were, this part. So the total state of the system is we got this qubit and then with this all together, right? So if I write everything out, it's just A0 plus B1, okay? And then you can just put it side by side. Like it's almost like a multiplication. This is kind of like doing this without introducing tensor product. But basically what is happening here is, let me put a half here. And then we can multiply everything out. So this is A0, 0, 0. And then A times the second term. Okay. So basically this is already tensor product. So it's actually nothing special about this. Okay. And then B1, 1, 1. Now, I want to rewrite this equation because I just want to separate which qubits belong to Alice, which qubits belong to Bob, right? But yes, I know the total state of the system is all 0, 0, 0 here. But I want to purposely distinguish these are the parts with Alice, these are the parts with Bob. So this side with Alice, this side is with Bob. Okay, and then I'll do the same thing for all the others. So basically what you end up with here is 1 over root 2, A0, 0, 0, and then A0, 1, 1, and then B1, 0, 0, and B1, 1, 1. Okay, now I got a 0, 0 here, 0, 1 here, 1, 0, and 0, 0. So I can substitute this equation inside. Right, so all this, let's just call this equation 1. So I will substitute equation 1 inside. So the total state now becomes what? Okay, so it now becomes, let's write this out. So 0, 0 is all this stuff here. So this is, there's a root 2 as well. So it's A over root 2, 5 plus 5 minus, and then 0. And then I do it this one, A over root 2, 0, 1. So it's psi plus plus psi minus, and then 1. And then this one is 1, 0. So B over root 2, psi plus psi minus 0, right? And then B over root 2, 5 plus 5 minus. Okay. So yeah, then now let us collect the terms together. The root 2, all I take out times another root 2, so outside it will become a half. But now we see that there's a 5 plus here and a 5 plus here. So I can just factorize the 5 plus here. So inside is going to be A0 plus A1. Okay. Actually, I said if no one is interested, you can leave. So I didn't check. Is no one around? Okay, so still got people inside. So if everyone already left, then I don't need to talk already. Then there's a 5 minus here and a 5 minus here. So let's put a 5 minus. So 5 minus is A times 0 minus B times 1. And then next is, let's do psi plus. So psi plus is B times 0, A times 1. Okay, and then psi minus, the last one is psi minus. Psi minus is B times 0. In fact, it's negative B times 0 plus A times 1. Okay, so this is actually, we didn't really do much actually. Alice got one state, Alice got one qubit that she wants to send to Bob, but she has an entangled pair shared with Bob. Okay, the total state of the system is like this. But the main point here is Alice got 2 qubits with her. What if you do the Bell measurement on these 2 qubits instead? Right, so you do the Bell measurement here. Okay, so if you do a Bell measurement, the eigenstates are the 4 eigenstates, psi plus psi minus, psi plus psi minus. That means you will get 4 outcomes. So Alice performs a Bell measurement. Right, you got 2 qubits, so you measure these two, and there are 4 possible outcomes. So that is, now you see what happens with entanglement. The first outcome is, let's say, right, because we don't know, all these are equal probabilities, so there is 1/4 chance to get this, 1/4 chance to get this, each of them 25%. We don't know what she'll get, but if she gets this, 5 plus, if she get this, right, that means the state becomes this. So by the entanglement thing over here, Bob, hang on, A plus B, Bob will get this state. A0, B1. Right? The spooky action at distance, Alice performed this measurement. Somehow the outcome at Bob is now this state. So you see, this state is actually the information that Alice wanted to send to Bob. So the state is now with Bob. Okay, so that is pretty interesting, right? So Alice started with psi plus. Alice started with this unknown state, right? Some information, A plus B. But we got entanglement qubit, so she does the Bell measurement on these 2 qubits. Somehow this information has been transported to Bob's side already. That is the teleportation. But the story is not over, because it seems to be not perfect. This is only one of the 4 possible outcomes. So what if Alice gets another one? So what if Alice gets psi minus? Then the Bob state now is not perfect, it's this one. So what do you do? So this is not exactly the same as the state that the information that Alice possesses, but we got quantum gates, right? We got the SG magnet. What if you pass this through the sigma z, right? So the sigma z will flip the eigenvalue of this, the one at the back, so I can change this into the state of Alice. So if she gets something different, then Bob needs to do something to recover the correct state. So if she gets the other one, then what happens the one with Bob? So the one with Bob is B0 plus A1. Notice that the A and B are at the wrong place, right? So we need to swap this position. So what is the something like the flipper? So you can use the flipper or the sigma x. Sigma x will give me A, change this to 0. This one change this to 1. So we get the state with Bob again. What time is it now? 8, 9. Yeah, so I think we can kind of finish everything within time. Then the last possibility is if she gets psi minus. So if she gets psi minus, then the one with Bob becomes this. Negative B0 plus A1. Well, it looks very different, but I can swap this. So sigma x, so the 1 becomes 0, B becomes 1, and then I do a sigma z to change it back. Okay, so it's still like slightly disappointing, right? It depends on outcome, and Bob needs to do a bit of extra work himself to get the correct state. So that is the issue over here, right? That is why, even though this is teleportation, but the information has not been sent faster than light, because we don't know what Alice will get. If we don't know what Alice will get, we also don't know which state does Bob get. So we also don't know whether the information with Bob is the correct one or not. The main point is Alice needs to tell Bob her measurement outcome. And the only way to do it is, well, classical channel. So yeah, Facebook to Bob, tell him what to get, right? And because the qubit with Bob after measurement, we don't know which is which. We need to wait for Alice to confirm with us what are the outcome. So depending on Alice's outcome, right, to recover the correct state, right, the one that we started with A plus B. So the first case is if Alice say she got 5 plus, psi plus, if she got 5 plus, then the one with Bob is already correct. So yeah, so Bob no need to do anything. Okay, so this one is just repeating what we did. So if Alice get this, then Bob needs to apply sigma z, right? And then 3, if Alice got psi plus, Bob applies sigma x. And then 4, if Alice got psi minus, then Bob needs to do. So the last one is a bit troublesome, it's 2 steps. So Bob applies sigma x followed by sigma z, right? So this means the state passing through sigma x first, then passing through sigma z. Then what comes up will be the correct state. So that is the idea of the quantum teleportation, right? So I don't know whether this is disappointing or interesting. It seems like both, because it is not like in teleportation in the sense that like one molecule get transported suddenly to another side. No, because Alice is holding the same qubit. Bob is holding one qubit, is the same the whole time, just that the state changes. Okay. So if we say quantum information, then the information is represented in the form of the qubit state. So it seems like if you share entangled pair, Alice just needs to do a bell measurement, and then tell Bob what she get. So then the state will be transferred over to the qubit. Okay, so in that sense, it's not like a teleportation, but like a possession, right? So the soul leaves the particle here and kind of possesses the qubit on the other side. Okay, so nothing is actually being transported over, it's just a state. So that is the boring thing of it. But the impressive thing of it is the spooky action at the distance, the entanglement thing. So like nothing needs to physically go from one side to another side, but Alice does something here, but suddenly Bob will know the information. Okay, and then another disappointing thing is, well, if Alice doesn't tell Bob anything, it's still no point, it's still useless, because you don't know whether the state is the one with Bob is this or this, right? Unless Alice tells Bob what she got, and then Bob needs to do the correct procedure to recover the correct state. Okay, so that is the main essence of the I missed this part. Correct, it's disappointing, right? It still needs a classical channel. Yeah, so hopefully we can get a flavor of like quantum teleportation. You know, every time, like if you see in the news, it's like, or people say in the movie, it's like something cool, use it to explain this. But you know, we spend the whole semester learning quantum mechanics, so we know how to do real quantum mechanics, like what real people does in real life. We know how to calculate, we know how this experiment works, and now we know for what we mean by teleportation is doing this. Okay, so yes, still need classical channel, unfortunately. Yeah, no faster than light communication. Exactly. So at this stage, we still can't figure out how to communicate faster than light. Okay, so wow, I'm over time, but that's it for today. So that was the very last lecture. So let me stop recording.